Let's calculate the electric field for the following distribution of charges. Suppose we have a charge plus q, and over here we have a charge of minus q, and I want to select a field point P at some distance away. Now, I'm going to choose a coordinate system where these particles are above and below the origin. This is the plus x direction. This is the plus y direction. Our usual unit vectors I hat and j hat. And now let's say that this distance here is a distance a over 2, and this distance here is also a distance a over 2. And I want to find the electric field at the point P. I'm going to call this one 1 and this one 2, just for our notation. Now, the electric field, by definition, at the point P, total, is the electric field of charge 1 at P plus the electric field of charge 2 at P. Now, those fields we've defined as K, Q1, R1P squared, R hat 1P, plus the other one, which is equal to K Q2 over R2P squared, R hat 2P. And remember, Q1 is equal to plus Q, and Q2 equal to minus Q. Now, the key here is what do these things mean? Well, let's introduce our notation. So we have here is R hat. This is 1 to P, and this is the distance R1P. And here is R hat 2P, and the distance here, we don't want this vector yet. We'll introduce that in a moment, but this is R2P. Now, what we'd like to do is express this vector decomposition. Can be a little bit tricky with our coordinate system, but we'll start with R hat 1P. So I'm going to call this the angle theta 1. And we'll make this point out here 2 field points, x and y. So once again, there's just vector decomposition. We have that R hat 1P. Well, it's going to have a cosine theta 1 I hat plus a sine theta 1 j hat. And if you notice that cosine theta 1, this is where it's a little bit tricky. Because this distance is a over 2, this height here, and let's just move this over a little bit, this height is y minus a over 2, I hat j hat. Y is that distance. This is a over 2, so that's y minus a over 2. And again, this horizontal distance here is x. So we have x over, and the Pythagorean theorem, I'll just write it as R1P for the moment, I hat plus y minus a over 2 j hat over R1P, and R1P is equal to x squared plus y minus a over 2 squared to the 1/2. Now, when we look at the other one, theta 2, it's going to be, argument will be very similar. This is y plus a over 2. That will be the only difference. And so I can write out that R hat 2P is equal to x I hat over R2P plus y plus a over 2 j hat over R2P, where R2P is equal to x squared plus y plus a over 2 squared to the 1/2. And now I'm in position to calculate, to just write down all of these terms. it's not a trivial expression. So we have the total electric field due to this positive and negative charge. There's going to be a lot of terms here. So we have the KQ, because Q1 is plus Q, over an R1P. Again, this is where that factor cube comes in. So there is X I hat plus Y minus A over 2 J hat. And the denominator is R1P cubed. There's a square factor there, one more there, and we have X squared plus Y minus A over 2 squared to the 3/2 power. And now we have to add in the other term. Q2 is negative. So we have a negative KQ over, and everything is the same except for this sign here. So we have X2 plus Y plus A over 2 squared, again to the 3/2 power, and the vector X I hat plus Y plus A over 2 J hat. And there is our total electric field for this configuration of a positive charge and a negative charge located on the y-axis, separated by a distance a.